students, myself Dr. Divya, Assistant Professor at Department of Chemistry, Institute of Aeronautical Engineering. In this session, we will understand the reaction mechanism of condensation polymerization and then explain the elastomers and types of elastomers with their properties and applications. So here are the topics. Let us understand the condensation polymerization, what is condensation polymerization, and different types of condensation polymerization depending on the monomers that are used. They are polyamides, polyesters, and resins. So these are the three types of polymers that comes under condensation polymerization. Then elastomers, what are elastomers and types of elastomers like natural rubber, crepe rubber, Buna S, its synthesis, then thiacol rubber and their synthesis properties and applications. So we will go in detail. So what is the condensation polymerization? So the polymers which form due to condensation reaction. There is some loss of byproduct that is going to take place. It is also called as step growth polymerization. Step growth polymerization. So condensation reaction takes place and is also called as step growth polymerization. And the polymers that are obtained by this reaction are called condensation polymers. So examples are nylon 6,6, terylene and bakelite. These are some of the examples which we use commercially most widely. So there are three types of polymers that are from the condensation polymerization: polyamides, polyesters, resins. So these are the three different types depending on the monomers that are used. So what are polyamides? The first one is the polyamides, polymers from which monomeric units are linked by amide bonds. So the bonding between the monomeric units is by amide bonds. So then it forms a polyamides. So the monomer should be a carboxylic acid and polyamide. So one of the monomers should always be a polyamide. Only then the polyamide bond will be forming between two different monomers. So usually dicarboxylic acids and amines are used. So this is how we will be selecting the monomer for forming a polyamide polymerase. So polyamides belong to fibers depending on their intermolecular forces. So these comes under in the classification, these comes under fibers. So as we see from the examples also, nylon is most widely used in the textiles. So nothing but due to fibers, fiber nature. Now let us go into the details for one of the example. So here is the polyamide polymer nylon 6,6. We have taken an example. So this is a copolymer. What is copolymer? When two different monomers are used, then it is forming a copolymer. So adipic acid and hexamethylene diamine. These are two different monomers used. Two different monomers. So therefore called as copolymer. So both these monomers can be obtained from butadiene. So this is the adipic acid, and this is the hexamethylene diamine. So if you see the structure also, diamine, 2 amine groups and 6 hexamethylene, that is nothing but hexamethylene. So that is how we take the monomers during the polymerization reaction. So and when the condensation takes place, so there is a byproduct forming, that is water, that is removal of water. So then it forms a polymeric chain. This is how the monomers keeps on condensed together, forming a polymeric chain. So nylon 6,6, various polymer chains are connected. So these chains, when the chains are forming, they are connected by strong forces. Strong forces are bonding called as hydrogen bonding. So hydrogen bonding is involved in connecting two different chains of polymer that is forming polymeric chains. So this is how the nylon fiber is forming. So the other example is the nylon 6. Nylon 6, which is a homopolymer wherein we are using similar monomeric units. Similar monomeric units. So that is caprolactam, a 7-membered cyclic amide with 6 carbon atoms. So during the preparation of this nylon 6, caprolactam is used. So how is this caprolactam forming? So cyclohexane, you know that this is the cyclohexane. When oxidation takes place, oxygen is attached, cyclohexanone is forming. Upon reaction with ammonium hydroxide in alkaline medium, there is a evolution. There is removal of water and it is forming oxime, and when it reacts with sulfuric acid, it forms caprolactam. This is how it contains a amine group and a oxygen group with 6-membered cycle. So this is how it is forming. So with this caprolactam is used in condensation reaction. So it first decyclation takes place by hydrolysis. What is decyclation? Removal of this cycle compound. So it undergoes hydrolysis and the chain on the circle opens. The circle opens. Open chain real polymer monomer is forming. So what is that? Aminocaproic acid. So this is the aminocaproic acid. This is how it is forming from the ring. The opening of the ring is caused by hydrolysis. So whenever it is opening the ring, it is forming aminocaproic acid. So under polymerization, it keeps on removing the water. The condensation reaction takes place and it removes water, and therefore polymerization takes place, forming the bonds between two monomeric units and ultimately forming nylon 6. This is how the self-polymerization takes place with single monomeric unit. So whenever there is a similar monomeric unit is used, then it is a homopolymer. So nylon 6 is a homopolymer. Nylon 6 is a homopolymer. Nylon 6 is a copolymer. Nylon 6 is a copolymer. So just remember this, that because of the use of different monomeric units, there is a difference in the fiber structure. Then what are the properties of these nylon fibers? They are linear structures in which molecular chains are arranged parallel to each other by hydrogen bonding. So in both the cases, hydrogen bonding is dominating, like between two different chains, hydrogen bonding takes place. So these strong intermolecular forces make them crystalline and impart strength, elasticity and high melting point. So this is why we use in many applications, because of its high melting point, elasticity and strength. So they are also chemically stable and resistant to abrasion. So because of this particular property, we are using for the tires application also. The sheet of nylon is applied in the tire manufacturing. So yarn is smooth and long lasting and can be used in spinning into a fiber. So fabrics are generally manufactured from this yarn that is created from the polymerization reaction of nylon. So this is long lasting because we know that when compared to other clothing, nylon will withstand longer time. And this fiber is tough, lustrous, moisture resistant and easy to dye. So it is because it is easy to dye and retains color. This is most important thing in the fabrics, because it is the color should be retained. It should not discoloration should not happen even in the heat or steam, because we dry the clothes in hot summer also. So it is the most important thing where nylon can be applied. So these are the applications: sport gear, fishing lines, combs or tooth bristles. This is, if for example, toothbrush bristles also are made up of nylon fibers. An engineering point of view, they are used in gears, bearings, jacketing electrical equipment, cords for tires. These are some of the examples for the nylon. So let us see the next one, polyesters. By the name itself, we understand esters. Ester is nothing but the monomeric units are connected together by esteric bond. So that is why it is called as polyesters. So the monomers used are polycarboxylic acids or polyols. So generally dicarboxylic acids and diols are used in the manufacturing of polyesters. So these are the monomeric units used. So these comes under fibers again. So we generally hear polyester clothing. So that is nothing but coming under the fiber classification, and this is the example for that, polyethylene terephthalate, that is PET. PET is an example for polyester fabric or the polymer. So if you see, this is a copolymer because we are using two different monomeric units. So it is called copolymer, terephthalic acid and ethylene glycol. So these two are different monomeric units that are used in formation of polyester. So therefore called as copolymer. So they are commercially called as terylene and has strong intermolecular forces. So if we see these reaction mechanisms, terephthalic acid, if we see, then ethylene glycol, there is a removal of water molecule is removed, and the formation of bond, there is a formation of bond. So that is how it keeps on multiplying, or the addition takes, the reaction takes place between two monomeric units. Reaction between monomers undergoes condensation reaction wherein water molecule is removed. Upon removing water molecule, there is a formation of polymeric chain. So between two polymeric chains, there is a formation of bonds. So these bonds are nothing but intermolecular forces that are between two different molecules, two different polymeric chains. So the formation of esteric bonds is creating polyester fiber. So what are the properties of this polyester forming? High mechanical strength and dimension stability, then very strong fiber, and will but however when it is wet it will lose some strength, and it is elastic in nature and possesses property of crease resistance. So this resistance is very important in any fabric because for long lasting time. So it is stable at temperatures of -40 to 100 degrees centigrade, and is shows creep and abrasion resistance and good insulating properties. So all these, most of the polymers are they are applied in all the insulating applications because of good insulating properties, and it also shows low absorption, water absorption. If you see our fabrics also, some fabrics like polyester, they absorb very less water, so drains, the water gets drains easily. So therefore the applications are like video and audio tapes, textiles, bottles for food and beverage. Then fiber can be blended into wool to form terry wool or cotton to form terry cotton. So these are some of the good examples for the PET or terylene. So if we see here also, there are granules that are used, then that granules are then molded to form the bottles, containers, and then plastic toys, containers, then synthetic carpets, so that the absorption of water is low, and the clothing, raincoats or something like that, then insulation between walls because it will keep cool. So these are the good examples of and applications for the terylene or the PET. Then third one of the forming from the condensation polymerization is the resins. So resins are very important because they forms the basic binding materials for different applications. So these are binding materials present with essential ingredients in the polymers. So they belong to thermosettings as per the classification due to their intermolecular forces. Then the example is the bakelite that we have already seen in the previous session. Bakelite is used for many applications. So we will see in detail how the bakelite is forming. So the condensation reaction of phenol and formaldehyde in the presence of acid or alkali catalyst at proper temperatures produce bakelite resin. So this is the main important step in the bakelite formation. So this is the ultimate one. The final reaction is between phenol and formaldehyde in the presence of acid or alkali catalyst at proper temperatures produces bakelite resin. So we will see in initial step by step what happens really. So initially phenol and formaldehyde reacts to produce mono methylol phenols. So this is phenol, this is phenol. So when phenol reacts with formaldehyde, it will form either methylol phenol or trimethylol phenol. So depending on the ratio of this phenol formaldehyde ratio. So this is very important. P by F ratio is very important. So depending on when it is 1:1 ratio, it forms monomethylol phenol. So the substitution of these groups is high when it is 1:3. 1:3. So when it is 1:3, it will form trimethylol phenol. Just remember that when it is 1:1, it forms one mono. When it is 3, it is trimethylol phenol. This is how the initial step takes place. So then what happens? In the second stage, this mono, di and trimethylol phenol are heated together. So to produce two types of straight chain resins. So when they are heated again, the condensation takes place. So how is it that condensation of methylol group takes place with hydrogen atom of benzene ring? So this condensation will remove water molecule. So and forms A stage. For example, if we see that A stage, so this is the monomethylol group. So then again it condensation takes place between two other groups. Then it forms B stage. So these two will again heated together to form a bond between monomeric units. So heating of stage A and B resin together obtains cross-linked bakelite plastic resin. So this is how the groups are combined together and the chain continues. This is the formation of bakelite resin, that is from this third stage wherein the mono, di and trimethylol phenols undergo condensation in the presence of heat and forms cross-linking bakelite resin. So what are the properties of this bakelite? They are rigid, hard and scratch resistant material. So mostly because of this hardness, they are used for longer period applications. So it also has good insulation properties, thermally stable up to 200 degrees centigrade, resistant to water and low flammability. So these are the good properties that a bakelite possesses. So these are applied in switches, plugs, switchboards, cooker handles, because we are seeing that it has low flammability. We are using in all these applications because there is a chance of getting heated up. So that is how we depending on the properties of the polymer, we choose for different applications. It is also used in the electric iron parts, telephone parts and homes. So these are the good examples, and also used as a bearing for the propeller shafts and rolling mills. So these are the examples or the applications of bakelite resin. Then next topic is the elastomers. So what are the elastomers? How are they classified? We will understand that rubbers are also known as elastomers. So these are high polymers which have elastic properties in excess of 300%. So just from the name itself, we can understand that elastomers is nothing but the polymers that possess elastic properties. Elastic properties having rubbers. So just we have to remember in this way. And for example is the natural rubber. Initially there are synthetic rubbers and natural rubbers. So nature is having all types of polymers. So a natural rubber, it has high molecular weight. So hydrocarbon polymer is also like hydrocarbon polymer having hydrocarbons in the chain or the network or the cross-linking. So presented by a formula of C for H8 taken X times. So this is how the polymeric chain consists. So example is like rubber tree. We obtain milk emulsion called latex. So if we see that there is a tree, rubber tree called rubber tree that contains latex. Latex. So this is nothing but milk emulsion. So it is like milk, and by tapping the bark of tree, it is the polymer of isoprene units. So the network consists of isoprene units. This is the isoprene CH2, C, CH and CH2 with methyl group here. So this is the isoprene unit, and latex contains isoprene units of about 2000 to 3000 monomers. So this is undergoes the polymerization and forms rubber. So this is the natural rubber that is present. So if you see in detail, like if you see this picture, there is a cut made here. So that is giving the latex out and being collected here. So collection of latex, initially the collection of latex is done. So that is nothing but the colloidal rubber milk from the rubber tree. Then the main constituents of this rubber latex is 25 to 45% of rubber, and remaining will be water, protein and resinous material. So what happens when there is protein along with the rubber, there forms a neutralized rubber particles because of this protein layer. This is the protein layer. The rubber material is covered with a protein layer. So if you want to process, we have to obtain some procedures and remove this, break this protein layer. So we will see in detail. Rubber latex is coagulated by using 5% of acetic acid and made into sheets. So how is it made? It is coagulated with 5% acetic acid, and the rubber sheets are cured under mild heat and then subjected for further processing. So whenever we obtain the natural rubber from these, so this natural rubber is then treated in different ways for further processing. So this rubber polymer is having a negative charge due to protein, and then treated with acetic acid. Acetic acid. Coagulation takes place. Coagulation takes place. That is how it breaks the membrane, protein membrane. So when the protein membrane is breaking, it will be feasible for us to process further and make sheets like this, and then apply for different applications. So there is different types of rubbers that are forming depending on the treatment. Then if we see an example, crepe rubber. So this crepe rubber is produced when the rubber latex is treated with sodium bisulfate and bleach to bleach the color and feed into the roller to make sheets. So this will make 1 mm or more thickness sheets and is dried in air at 40 to 50 degrees centigrade. So this is how the drying, this is the rolling takes place and dried at 40 to 50 degrees centigrade. So for any rubber to form, initially a coagulation step is required, and depending on treatments, different treatments, the different types of rubbers formation takes place. So the preliminary staining and the weighing of latex, then bulking or standardization, then addition of sodium bisulfate. So this step there forms a crepe rubber. Crepe rubber. So then again the bleaching, coagulation. So depending on our application, we will be treating the rubber so that it forms different colors. So this dried sheet of rubber is also known as smoked crepe rubber. So this prevents, what happens when it is treated with sodium bisulfate, prevents darkening of pale crepe due to enzymatic. So there will be enzymatic reactions that takes place. So the treatment is very important to avoid those. So delay in incorporating the chemical will discolor the crepe rubber. So it will become dark colored. So there are some applications like here are the rubber that is used as the bags, and also some footwear that are made from the crepe rubber. So the other process is the next process is the mastication. So rubber becomes soft. So the initial latex that is taken is agitated mechanically. It means they're shaked mechanically so that it becomes soft and gummy mass when it is treated mechanically. So this process is called as mastication. So this is followed by addition of certain chemicals. So this after this mastication, chemicals are added and then again introduced into rollers for rolling purposes to make into sheets. So after mastication is completed, the rubber mix is prepared for vulcanization. So depending on the applications, again the other treatment is depending on applications, other treatment vulcanization is done for the processing. So let us see what we will be doing in this. So in the vulcanization, the raw rubber is treated at 100 to 140 degrees centigrade with sulfur. So there is introduction of sulfur into the polymer, the rubber latex, so that it forms some chains. If, for example, if these are the isoprene units treated with sulfur, there are the sulfur cross-linking, sulfur in between these chains, sulfur introduced between the chains. So they combine chemically at double bonds of different rubber springs and form cross-linking between these chains. So this is how the sulfur is introduced into the rubber. This cross-linking brings stiffen. So whenever we want a stiff rubber to form, then we introduce sulfur into that. If we see this application, rubber tires, so tires needs to have should be resistant for the wear and tear. So therefore we have to stiffen that rubber. For that we are introducing sulfur into the cross-linking or the chains. So the stiffening of rubber by anchoring and consequently preventing intermolecular movement of these rubber springs are nothing but the chains. So the amount of sulfur determines the extent of stiffness. So depending on the stiffness we require, the amount of sulfur also to be added. So what are the properties? So whenever we introduce sulfur into the rubber springs, then it will increase the tensile strength, then better resistance to moisture, oxidation or abrasion. So therefore we are using in most of the parts of automobiles. So in if we see this picture, we can know that there are a lot of components that are including vulcanized rubber, and it is also resistant to organic solvents like carbon tetrachloride, benzene, petrol, etc. So these are good properties that a rubber can possess if it is introduced with sulfur. So it also has slight thickness and low elasticity. So these are some of the properties. Then because of this elasticity and resistance, they are applied in many applications. Examples: manufacturing of tires, then tank linings in chemical plants. As we are saying, it is resistant to organic solvents. The chemical plants can be coated with this rubber, so that lining with this rubber, so that it is resistant and leakage proof. And also it reduces the machine vibrations, even in the industrial and domestic applications. When there are huge machines running most of the time, there are some stoppers that are kept at the bottom, so that the vibrations can be reduced. And also this is an example of domestic usage. However, in the industries, when there are two metal parts that are used in clamping, for example, these clamps, these two are metal parts. So in between we can use this rubber, so that there is no stress that is applied on that metal part. So that will reduce the stress and also strain due to that, and the noise also is reduced. Then the foam rubber is used in the cushions and mattresses. So this is an example of foam rubber, cushion and mattresses, wherein we use a foam type of rubber in these applications. So these are the good applications of rubber that is being manufactured with different treatments, and depending on the strength or the tensile the strength we require, we have to include the sulfur so that it becomes vulcanized rubber. Then there are different types of other rubbers like synthetic rubbers that are made from rubber. So these are the examples: styrene rubber or Buna S rubber. This is the other name of styrene rubber. So how is it formed? From the copolymer of butadiene. It is a copolymer. It is called different monomeric units are used. Different monomers are used. What are those? Butadiene and styrene. Butadiene and styrene. So in earlier days, sodium was used as a catalyst and at heat temperature. So the name Buna is nothing but butadiene and sodium that is used, and S is the styrene. So this is how the name is obtained. It is also called as government controlled styrene rubber or styrene butadiene rubber. So these are the different names of Buna S or the synthetic rubber examples for the synthetic rubber, styrene rubber. So the Buna S is the first synthesized rubber, synthetic rubber that is synthesized and is prepared from copolymerization of butadiene and styrene. If you see this reaction, butadiene and styrene at under heat, when it is catalyzed by sodium, forms a polymeric chain of Buna S. Polymeric chain of Buna S. This is how the polymerization takes place. So what are the properties? It is strong and tough polymer, and this rubber can be vulcanized with sulfur and is a good electric insulator and possess good abrasion resistance and resistant to chemicals and high load bearing capacity. So these are nothing but these can be used in different applications of automobiles and industries because of these good properties. So they are used in tires, footwear like shoes or soles, and then making wires and cable insulators and floor tires and tank linings. So these are the good applications. So if you see these aircrafts or the transportation systems that have Buna S rubber that is used in the tire manufacturing, then some O-rings so that contains Buna S that can be used, and also the shoe or the shoe or the sandals or the chappals made from these rubbers because of their resistance to abrasion, so that it do not get wear and tear easily. So the other type of synthetic rubber is the thiocol rubber. So it is prepared by condensation polymerization of sodium polysulfide and ethylene dichloride. So these are the two different monomers that are used. Different monomers used to form thiocol rubber. So therefore it is called as a copolymer. So these in these elastomers, sulfur forms a part of the chain. So we do not really introduce the sulfur. It is from the monomeric unit that is already present. So therefore ethylene dichloride, when it is reacting with sodium polysulfide, it forms a thiocol A. Thiocol A with a byproduct of sodium chloride. This is how it is. Thiocol A is formed. So this is another type of synthetic rubber. So because of this sulfur, there is some properties varying. So let us see the properties. So these rubbers possess strength and impermeability to gas. So they have good strength and they do not permit any gases. So this rubber cannot be vulcanized because its structure is not similar to natural rubber and cannot form hard rubber. So it is smooth and flexible. And it also possesses good resistance to mineral oils, fuels, oxygen, solvent, ozone and sunlight. So these are the better properties that it possesses. So depending on these properties, they are applied. It is used in different applications. So fabrics coated with thiocol are used for barrage balloons. So these barrage balloons are made from the thiocol rubber, then it is used in the as a solid propellant fuel for rockets. So even there now this is the thiacol, so that is made, and the solid, it is used as a solid propellant fuel. So this is filled with, all this gap is filled with thiacol, solid fuel. So because we are not using any liquid here, it is called solid fuel and can be used in the propulsion of that rocket. It is also used in making gaskets and hoses. So these are the good applications for gaskets and hoses. Then printing rolls like these, and containers for transporting solvents. As we have already seen in the properties that it is resistant to solvents and gases, that it can be used in transporting these solvents. So the containers are made from thick or rubber. Then diaphragms and seals are in contact with the solvents. So these can also be used in the diaphragms or the seals, so that there is no leakage of these solvents. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.